I just wanted to take a minute to summarize some of the important things that we covered today and emphasize a last point that we went over a little too quickly at the end of class today. The main idea that we started with was that work was equal to, as you've seen in physics, force times distance. The challenge we have to work with now is that the force being exerted on the object might not necessarily be going in the direction that the object is traveling. If you're pulling something up a hill and you're not pulling it straight up the hill, you're standing up and pulling it at an angle. So what we found when we used our notation was work was going to be equal to the magnitude of the force parallel to the direction the object is going in times the magnitude of the direction you're going in. And we played around with this a little bit, and what we know is that this magnitude right here is the magnitude of the force vector itself cosine the angle between the force vector and the direction you're going in. So now we have work is equal to this, and then also the d is still there, the magnitude here. If you rearrange this, you end up with f d, the magnitude of cosine theta. But from our definition of dot product, we know that this right here, this is, when I say this, I mean this side right here, we know from yesterday that that is one of the definitions of the dot product of f and d. So as was mentioned at the end of class, in the example we did, we knew the problem gave us the magnitude of the force vector, the magnitude of the direction, it was like 120 and 20, and the angle, which was 30, so we could figure out the work that was done, and we had to use this right here. But if we had the force vector itself, if we had the actual components of the force vector and we had the actual components of the direction vector, which we did in this case, but we did not have that, as I think Tori asked at the end of the class, what would you do? You could just take the two vectors, dot them together. So you would take your two known vectors, multiply the components, and add them together. So once again, we know work is equal to force times distance, but the force needs to be in the direction of the distance. That's how you did it in physics. If the force is not in the direction that the object is traveling in, you need to find the magnitude of the vector, the force vector, parallel to the direction you want to go in, and multiply it times the magnitude, the distance you're traveling. That is the distance you're traveling. But we know that the component in this d direction, this magnitude right here, is equal to the magnitude of f cosine theta. So this just gets replaced right there. But we know that this can be rearranged to this, and this is the definition of dot product. So if you have the actual vectors for force and your displacement, you can dot them to get the work. But if you only have the magnitudes, if you only have if you have both magnitudes or one of the magnitudes and the vector, so effectively you just have the magnitudes, you need to use this one, and that's what we used. But if you have the vectors, use the dot product. That's the moral of the